Struggling with subnetting and binary conversions? What if there was a magic number that could simplify the process? In this video, we'll reveal a decimal-based method for calculating network and broadcast addresses without touching binary. Whether you're studying for a certification or just want to master subnetting, this is your ultimate guide to making networking easier. Ready to unlock the secrets of subnetting? Let's dive in.
Network administrators often need to divide networks into subnets to provide scalability. For example, a business that occupies a 3-story building might very well divide its network based on the number of floors. This also makes it possible to limit the propagation of broadcasts because the broadcasts remain on the local network. A subnet is simply the fact of dividing a large network into a smaller network. It is thanks to the subnet mask that it is possible to perform this division. For a router, the mask makes it possible to distinguish the part of the address used for routing and those which can be used to number interfaces. This is how routers can establish communication between devices which belong to different subnets. As an example, we will take a Class B IP address, 172.168.50.25, with its default subnet mask, which is the 255.255.00. A subnet mask is a 32-bit combination that is used to route traffic through a subnet. It allows us to define in the IP address which part corresponds to the subnet and which part corresponds to the host. An IP address has two components: the network part and the host part. The subnet mask is used to divide the host part. The first part will identify the subnet to which the devices belong, and the other part will identify the hosts. In this example, let's say we want to split our Class B network. The default mask for a Class B is a /16. That is, the 16 first bits are reserved for the network part, and the last 16 are for the host party. Our network therefore includes addresses from 172.168.00 to 255.255. To divide this large network, we will use a mask /20, that is to say 255.255.240, 0. With this new mask, it means that the first 20 bits are intended for the network part, and the 12 bits remaining for the host part. The subnet mask is created by placing a binary 1 in each bit position that represents the network part of the address, and a binary 0 in each position that represents the host part. That is why with a mask in 20, we have only 1 in the first bits of the mask, and the rest contain only 0. If we translate it into decimal, we find 255.255.240, 0. With this new subnet mask, our IP address, 172.168.50.25/20, is part of the network that goes from 172.168.48.0 to 63.255. Having a different prefix changes the host range for each network. We will now see another example with the IP 101.20.70. Associate with a subnet mask in /26, that is to say 3 times 255.192. We would like to know the network address and broadcast of this IP. For that, you must write the IP address and its mask in binary. In the subnet mask, the 1 represents the network part, and the 0 represent the host part. When we talk about separation, we are talking about the separation between the network part and the host part. That is to say, between the 1 and the 0. To find the network address, change the bits to 0 to the right of the separation of the IP address, which gives us the network address in decimal 1012064. For the broadcast address, it is the same thing, except that the bits must be changed to 1 after the separation, which gives us in decimal 10120.127. The usable IP range therefore goes from 10165 to 126. The network address and the broadcast address cannot be used for equipment, and this is how we calculate the network and broadcast address using the subnet mask. If you are a bit allergic to binary, I have very good news for you. There is a method which allows us to know the network and broadcast address from an IP and a mask without going through binary conversion. This method is very useful for the Cisco exam because it saves a lot of time on IP conversion questions. This method is based on a magic number. It is simply a calculation made from the significant byte of the mask. For example, we will take the same IP which we previously converted into binary, the 1012070, with the same subnet mask, the 255.255.255.192. Here we see that the significant byte, the one in which the separation takes place, is 192. Match the fourth byte. We will subtract the significant byte from the magic number. This number, 256, remains the same for all conversions, which gives us 256 minus 192, which is equal to 64. Now we will write all the multiples of this result up to 256. The multiples of 64 are 0, 64, 128, 192, and 256. The network address corresponds to multiple less than or equal to our fourth byte of our IP address, that is to say less than or equal to 70. In our subnet mask, the significant byte is the fourth, the 192. This is why we use the fourth byte of our IP address. The first multiple, less than or equal to 70, is 64. Our network address is therefore 101.20.64. The broadcast address, which corresponds to the last IP address of a network, will be the following multiple minus 1. The multiple which follows 64 is 128, from which we subtract 1 to find 127. Thus, the broadcast address is 101.20.127. If the significant byte was the third, it would have added a 0 for the network address and 255 for the broadcast address. It comes down to binary, passing all the bits to 0 for the network address and all bits to 1 for the broadcast address. As you have seen, no binary conversion was necessary. We will take one last example. The same IP, but this time with the mask 255.224.00. We see here that the significant byte, the one where the separation takes place, is 224, which corresponds to the second byte. We subtract 224 from our magic number, which gives us 32. The multiples of 32 are 0, 32, 64, 96, 128, 160, 192, 224, and 256. In our mask, the separation took place on the second byte. The network address is therefore the last multiple of 32 equal to 1. It is the multiple of 0. The network address is therefore 10000. The broadcast address is the next multiple, minus 1. The next multiple is 32, from which we subtract 1 to find 31. The broadcast address is indeed 10.31.255.255. You can see that 0 has been added for the network address and 255 for the broadcast address. It comes down to binary, passing all the bits to 0 for the network address and all bits to 1 for the broadcast address.